Section 7.4, we're going to discuss arc length. So we're going to start this conversation just discussing the length of a straight line segment. All right. So if we have a line segment and we know the x and y coordinates of its two endpoints, then we can calculate the length of that line segment just using the distance formula. And we have x squared minus x. X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 all squared. And then we take the square root of that, we get the length. Okay. So what we're going to do now is we're going to try to take that concept and expand it to finding the length of a curve. All right. And just like we did with area and we did with slope, we're going to start this using the idea of breaking this thing up into parts and then using more and more parts to get a better estimate of this length. So you can see here that I've split this curved this length of curve here up into 4, in this case, straight line segments. So I have L1, L2, L3, and L4. And if I add those all up, I will get an estimate of the total length of this curve. Right? And obviously we could make the approximation better if we used more segments. Right? So we would get less error in each length we calculate. So in kind of the setup for, we're going to continue on to the next page, think about a given line segment that we use. Right? Now this would be the change in x, and then this would be the change in y, the delta x and the delta y. Right? So we could find the length of that straight line segment using the distance formula we talked about, but now instead of x2 minus x1 and y2 minus y1, we can just call those delta x and delta y. So let's take a look at how that will look when we do that. All right. So for a given line segment I, we have some change in the x value and some change in the y value, and the length of that given line segment would be the square root of delta x sub I squared plus delta y sub I squared. Right. So I'm gonna rearrange this a little bit, and it's not automatically intuitive as to why I'm doing this. This is kind of one of those, I know where I'm trying to get, and therefore it helps me figure out how to get there. Right. So I am going to take the second part here, the second part underneath the square root, second part of that sum, and I'm going to multiply it by delta x sub I squared. So I'm really multiplying by a form of 1 here. But I'm going to group the delta y sub I and the delta x sub I up into a quotient and square that whole quantity, and then I'll have this delta x squared multiplied by that quotient. Now look at what I'm going to do here. I'm going to take, inside the square root I have a delta x sub I squared and a delta x sub I squared factor in each one of these terms inside the square root. So here I factored out that delta x sub I squared. So I have 1 plus just this delta y sub I over delta x sub I all squared times the delta x sub I squared. Now I can separate this out. I have the square root of delta x sub I squared. I can bring that outside the square root and just have delta x sub I. All right. It still might not be obvious why I'm trying to do that, but it will be in a moment. Okay. So the arc length, the total arc length, is just this. Remember, this is the length of one of our small line segments. Right. So the total arc length is approximately equal to adding up all those small line segments. And if we use more and more line segments. In other words, we have the limit of delta x approach 0. There's other ways we can write this. The most common would probably be to have n approach infinity. The number of line segments that we use could approach infinity. And really, you could also say delta y is approaching 0 as well. Although since delta x is the independent variable, we usually use that. All right. Now if you look carefully at this and think back to when we talked about the definite integral, this looks a lot like, this is, a limit of an infinite sum, which is very much how we got the definite integral. So it's kind of a similar process. Here I have delta y over delta x, and I have my delta x out here. Delta x is approaching 0, and I have the number of these line segments approaching infinity. And what I get is a definite integral. Right? So I have from a to b, so I have to think about what x value I'm starting with and what x value I'm finishing with as I move from left to right, my lower and upper limits. So I have the 1 here, and if we look at this, as these deltas become smaller and smaller and smaller, they become differentials. And dy dx is just another name for f prime. Right? So we could just as easily write this as 1 plus dy dx squared dx. And of course, this delta x sub I also, as it gets, each one of those get closer and closer and closer to 0, when it becomes part of that definite integral, it turns into a dx. So all we really need to do to find the arc length, we need to be able to find the derivative of the function itself, whose length we're trying to find, and then we need to apply this definite integral to the square root of 1 plus that derivative squared.